Hello, everyone. Welcome back to the AAS YouTube channel. And this is the good stuff. This is the AAS Journal Author Series. And I'm super happy to have Patricia Hernández-Reséndiz with us today.
Hi, Frank. Thank you for having me.
Oh, well, thank you, Trish. It's great to have you. What is your geolocation? Where are you at?
I am from Mexico City. I am living here right now in the pandemic situation in a very huge city, but we're fine. We're fine.
What is the population of Mexico City these days?
Oh my God, this is a very big question because every time people ask me that question, and every time I forget the number.
Say
But
6 to 10 million.
I think like it's 8 million, but if you have the all the metropolitan area, it's like 16 million.
Wow. Okay.
Yes, it's a lot of people.
Wow. So obviously you're not in your office. So is UNAM shut down for the pandemic or?
Yes, exactly. We shut down in March, the last March, and then we came to our homes to work, and for experimental activities are very important and difficult because all the laboratories are closed now, and we don't know when we will return.
Okay. Yeah. It's a bit more of a problem for experimental observational work, which we'll be talking about here very shortly.
Yeah, actually, it's better for me in a very in a very particular way because I was doing my thesis, my PhD thesis, and then I finished it, and now I will graduate.
All right.
Thanks for the pandemic.
All right, Dr. Trish. Do you have a defense date set yet?
No. I think that for all the bureaucracy and all that stuff, I think that in January will be my exam. Yes,
okay.
my defending.
Okay, cool. Very good. So Trish, what do you like to do for research?
Yeah, well, it's a very important and emotional for me this paper because I started to work in this research when it was born. The experimental device wasn't exist, and then when I entered, I realized all the stuff, the difficult stuff that you have to do when you want to create a new machine. Then we expected to have a lot of budget, for example, for buy all the how to say it, all the stuff that the machine needed. And then we spent a lot of time, a lot of years to build the machine and to get the perfect way that that works for the things that we want to do. And this machine is how do you say it? Is built to do experimentally chondrules and micrometeorites.
Okay.
To see what happened physically with that kind of spheres, mineral spheres, in the process of the formation of them. For example, in the chondrule formation, we want to know the temperatures and the pressure and how very parameters are how do you say it? Are involved. Yes, are involved in the textures, in the final textures of chondrules and micrometeorites also. And for micrometeorites, how for example, how time and how temperature they need to have that textures, and we want to reconstruct the natural chondrules and micrometeorites with with a laser. That I think that this is one of the goals of the very huge goals of Citlalmitl, is that we use a laser. Normally, people in another experiments, they use a furnace, and we use a laser, and the laser gives us the opportunity to control very well and with very huge precision the energy that we put when we melt the minerals.
Cool.
And well, this is an introduction, because the paper show exactly how to we create the machine, Citlalmitl.
I'm sure I will butcher that when I say it. All right, that was a great intro. So let's get to this really lovely Planetary Science Journal article. So a nice thing about the Planetary Science Journal article is it's open access, so you can get the official version right from the journal itself. Yes. And this will be Citlalmitl, a laser-based device for meteoritical sample fabrication with arbitrary thermal histories. And Trish, take us away.
Perfect. Well, then we use a CO2 laser that irradiate at 50 watts of power, and it's a huge energy, and it's known that this kind of lasers can melt minerals very well, silicates particularly, because chondrules and micrometeorites, there are a lot of them that are formed of this kind of minerals that are pyroxene and olivine. And then we want to reproduce and to know about the models. Like, it's like to prove that models with Citlalmitl and exactly with the thermal histories. Then we want the goal is that we can prove every thermal history that one or another model propose to the formation of chondrules and micrometeorites. Cool. Then Citlalmitl was built for that reason. We took a lot of time to do that, because we wanted that the thermal histories could be controlled very well, and that was the point that took a lot of time to do it. Mm-hmm. Then this device now is working very well. Well, now, no, because it's the pandemic situation here. But if we shut on now, the machine is working right now very well, and is doing the things that we want to do. That is reproduce the thermal histories that we can program it, and then to prove the models, the different models to atmospheric entry for micrometeorites and to control formation. And then if you want to pass to the first figure.
Sure. Let's go. We talk a little bit. Slide down to figure 1. And there we go.
Perfect. This is a diagram of Citlalmitl. Of course, Citlalmitl is a Nahuatl word that means meteorite. Huh? And we thought that was very beautiful name for the machine. And well, this diagram shows that the different parts of the device, how we can control the power of the laser, because we have a power detector that is the D that you can see there in the image, and we use a beam splitter just for split the beam, but just a few part of the power, and then we use the two lenses to point the laser in the sample holder, that is the A, that is inside of vacuum chamber, and in the holes of the sample holder we put the silicate grains that will be irradiated with this laser, and well, we use a mirror that can move in the X way, in the J way, to point the laser beam in the different different how to say it, holes, in the different holes of the sample holder. Mm-hmm. And we also can measure the temperature with a pyrometer in situ. Then we have the thermal histories measured in the same time of the formation of the spheres, and then we can also know if the thermal histories are controlled or not. And well, this is all the machine is like a very big and is situated in the Instituto de Ciencias Nucleares, that is Nuclear Science Institute in UNAM here in Mexico City. And well, we do that with a no so huge team. We are 5 people, and but we we have very different how do you say it, base knowledge, because 2 of them are optic physicists. One is an astrophysicist, another is a geologist, and I am astrophysicist also. Then it's a very multidisciplinary project that can help us to learn about many other sciences that are related to, but I think that this machine shows very well the multidisciplinary thing that science can give us.
Let me ask a question. When you mentioned the spherical grain sizes, are these things micron size? Are they millimeter size? What are the sizes of the targets?
The size of the targets are hundreds of microns.
Hundreds of microns. Okay.
Yes. Yes.
Mm-hmm. Okay. Very good.
Perfect. Then we can go to the other figure to show you.
Let's slide down to figure 2.
Well, this part of the paper shows the energy control of the laser, and for me, for example, this figure is important because when you don't know about lasers too much, maybe you can be confused about the things that and the parameters that lasers have. And one of these is the duty cycle, because the duty cycle in the principal time, I thought that the duty cycle was like the same like power or something like that, but then I understand that the duty cycle is the thing that we can change and have a direct relationship with the power. And that relationship can give us the opportunity exactly to manage and control the energy that we can put in the samples. Then this image shows that how to what is the difference if we put, for example, 30% of duty cycle or 90% of duty cycle in the time, and that relationship give us another relationship with the power, and this is very important for the goal of Citlalmitl.
So the power in each pulse is the same.
Exactly.
What you're controlling is the time that that power is applied.
Yes, it's not exactly the same because the duty cycle is a percentage, but it's related with the power. Then, for example, if we put 90% of duty cycle, the power of the laser can reach it more quickly.
Yes.
If in comparison with the 30%.
I'm with you. Yep. Good. Thanks.
Yes. And the figure that is below that is the variation of the size of the spot of the laser, and this gives us also the opportunity to change the energy that is irradiated, because if we put the laser beam very small, the energy is more controlled in one point. Right. And if we put it in a bigger area, you can irradiate more area, and for example, to melt the sample more homogeneously.
Right. So what is Z? What is the
C is the position. No, is the position of the we have a motor. This is a motor, like it seems like a pen that you can move it, and you can move it in the C axis.
Okay.
And this is the position that depends the spot size with the position of the motor.
Got it.
And the motor move one of the lenses of Citlalmitl.
Aha, I'm with you. Okay.
Yes.
I'm with you. Good.
Then the next figure, it's yes. The next figure shows about the flow chart of the program that we do for control Citlalmitl, because more like now you know that there are many human errors that we can make when something experimental work are no. Then we want to control to program all the stuff in Citlalmitl, all the experimental things and the measures, to take the measures also, to do Citlalmitl, a huge machine that have the opportunity to be controlled at the distance. No?
Yep.
Then we do the program. Obviously, there are many versions of the program, because, for example, when we started to build it, we haven't all the how you say it, all the
calibration, the building,
no.
testing, verification.
All the verification, no. All the, oh my God.
You'll think of it.
Oh, even in Spanish, I forgot the word. How do you say it?
I may vaguely be able to know that.
The things that are the Citlalmitl is composed by oh my God.
That's okay. Keep rolling. When you think of it,
all the parts that are composed with Citlalmitl. Well, then the automatization of Citlalmitl was one of the important things that we wanted to create with Citlalmitl, and then this flowchart shows how to work the program now, and then all the adjustments that we can do with the program. For example, the parameters of profile selection, because we can program different profiles of irradiation profiles, and then we can choose one of them when we do an experiment. Then also we are very worried about the calibration of the points of melt, because we want to be sure that the melts will be well melting. Then that stuff we want to do with press one button, no?
Yes.
Then and the machine record all the measurements of each part of the measures, for example, of the barometer, for the pressure, for the power of the laser, and then we can then compare if we really control the thermal history of our samples. And that's the diagram of how to work the program.
So once you irradiate a sample,
yes,
how long does that experiment run? So you heat it up and then you cool it down. How long is that time? Is that 10 seconds? Is it several minutes? Is it an hour?
We can program it.
Okay.
And we are based in the formation control models and the entry parameters models of micrometeorites. And for example, in micrometeorites, we need very few seconds to irradiate them. Then the maximum time to irradiate one sample that we can consider it like micrometeorites is 2 minutes.
Okay.
And for chondrules, we are proving with many different periods. For example, 10 minutes. 10 minutes, I think that is the most huge period, but we can also irradiate by 5 minutes.
Mm-hmm.
And I think that the better is like 3 minutes, more or less, but also we can program the cooling rate that we want to prove. And this is very important for the textural, the final texture of our samples. And for example, maybe there are irradiated with a very huge energy, but just 1 or 2 seconds, and then the energy slows down very slowly, or not. It depends of the things that we want to prove.
Right.
But the time that I say is the total time, isn't it? But
okay.
We want to prove, then we can prove very different ways to irradiate them.
Okay, cool. Let's slide down. There's the answer to my question. If I just waited a minute, it was right there. There's
exactly.
the time.
This is the answer.
That
yes.
was people.
In this paper, we show these 2 profiles, but in the future we have actually now we have another new profile, but in the future, actually we can prove any profile that one model can give us to prove if it really can reproduce chondrules or micrometeorites. Then, for example, the first profile show a profile that start very quickly to the top of the energy, and then is a irradiation, constant irradiation, and then slow down very quickly. Then that example, for example, is one example, but we can manage the velocity of the decay. And then the second profile is based of a shockwave model, where that is a model that is a very first of all is one of the better models for controls, for the formation of controls, and also for the atmospheric entry for micrometeorites. This needs this profile need more work also, but the important point is that it start very quickly also, and then the decay is slow, and we want also to have the temperatures to melt the sample.
Right.
And this is a very physical, it has the physical ways and the physical, how do you say it? The physical explanation of controls and micrometeorites that the other one doesn't have. The other one was like a profile to prove many things to in Citlalmitl when it was building, and to see if we are achieving the energy control that we want to do. But in the future we can do many proofs with many profiles.
Right. Cool. And it looks like here in table 1 and 2 we have some target materials.
Yes, is the composition of the target materials, and we use olivine and feldspar. That one we choose these materials because they are very important materials for contours and micrometeorites, but we also know that they are not very realistic, because the composition of contours and micrometeorites have more feldspar and nickel and iron, but these two could help us for a first approach for the controls and micrometeorites formation.
Yeah, so you construct these targets, you build them.
Yes.
Yes, I think that's important. Okay.
Yes.
Okay. We got some targets. We got a fantastic laser. Here we have.
There are experimental parameters that we put.
Yes, very good. And let's see what we get. Awesome. Nice big figure caption. Love it. Okay. All yours.
Yeah, well, these are 4 samples that we show, because we think that are very characteristic about all the samples that we could create at the moment of the paper was wrote. And one of the important things is to see the profiles, because, for example, in the first 2 samples, we saw that the machine wasn't controlled very well, the energy, and the temperature. But when we work with more with the program and with Citlalmitl, we can see in the two samples below that the control can be very well controlled, the profile, because then there we can see in blue the temperature measurements, and in black is where are the program profiles.
Right.
And when you see the red one is the power, the measurement of the power, and that could be possible because 2 years after the machine was working, the power measured arrived. Then we can put it in the device, and in the diagram now appeared it, because now is part of Citlalmitl. And this power detector can give us the opportunity to see if the things are working like we think that they are working with the power. And we can see also then that the power and the temperature have the same trend. Then can give us the sure. Then we are sure that we can control the temperature history with the programming profiles. And this is one of the goal of Citlalmitl now, because now we can also prove many profiles with this. And then we can talk about the samples. For example, the first sample have crystallographic texture that can give us the cryptocrystalline texture, and there are chondrules and micrometeorites that have this kind of textures also. Then we can say that now we are able to reproduce analogs that are very similar to chondrules and micrometeorites, natural chondrules and natural micrometeorites. And the second one, for example, if you see it with a very huge contrast, it's very beautiful, because you can see all the bars that are formed, the olivine bars that are formed in that sample. And also we can see and measure with the chemical analysis how iron and volatile materials are lost in the irradiation period. Then, for example, for that reason, I put the C and the R in the edges, and the C in the center, because in the last table we see the chemical composition, and we see also that the iron is conserved more in the edges, because it was lost during the irradiation. Also, another thing that is important to say is that there are many relict grains that stay in the samples. For that is a huge relic grain. And there are other ones that are not so huge, but it's important to know how to when it appears and when it doesn't appear, and because also they can give us information about the time of retardation and the temperature that we need to melt all the sample, for example. All the things that, for example, we want to know about that is that how influence the irradiation of the sample and the heating of the sample. If we put many grains of silicate, or if we put just one grain. And for example, in the where you see that there are relic grain very, very huge, was because there are many grains around them. Then, like, the energy could spread and could divide it for all the grains, and then it have a how to say it, a relevance there in the last texture that we can have.
So I think it's interesting in this this one, it was given a shock profile.
Yes.
And you've got this very interesting stripes.
Yes, yes, and another important thing in that sample is that we use also feldspar and olivine in a combination, and that gives us a pyroxene final composition. And there are, for example, in the literature, show that was very, very difficult to reproduce radial pyroxene controls, for example, because just olivine or just pyroxene wasn't able to reproduce that texture. And we saw that if we do this combination of initial material, we can reproduce them. But also we want to prove with many other combinations to see what happened there, and if we can also have different textures like this. But there are a lot of samples like this one that are very, very beautiful when you see it in the microscope with your eyes, because the colors are very beautiful. And yeah. I wanted to have one of them here to show you, but I can't. Because they are in the laboratory.
Rats. Very cool. Very
yes.
cool. So we got more of those, and then we end off. So, yes. Lovely work. Congratulations.
Thank you so much.
And where do you go, Dr. Trish? And where does the community go over the next 5 years with this? You mentioned, other experiments which will surely take place. Are there other theoretical calculations that could augment the experiments being done? And then, of course, at the end of the day, you want to be able to take these experiments and put them in sort of the large-scale picture of solar nebula formation, whether it's our solar system or exoplanet solar formation. So where do we go over the next 5 years? Where should we go?
Well, first of all, we want to prove with more realistic models from the formation of chondrules and micrometeorites. Mm-hmm. And we want also to prove with a more realistic initial precursors, talking about the composition. Mm-hmm. Then now we are one of my advisors doesn't want to crush a real meteorite, because was like, oh no. But now we know that it's very necessary in this period of the machine. And also we want to Citlalmitl can have another ways to use it. For example, we want to irradiate also with meteorites to form the cores. How do you say it? The enter cores that was formed when they enter in the atmosphere. Yes, that is a course there.
Yeah, they have a core and then they've got an outer melt region.
Yes, exactly. We want to form them to see the temporal profiles there. And also there are another idea to see what happened with different atmospheres when we radiate the atmospheres with the laser, to see chemical changes with that irradiation, and that can give us also, for example, information about the atmospheric changes in the primitive Earth. There are many ideas that we can use Citlalmitl with, and are very interested. And actually, I also say that this kind of work inspired me too much, because one of the things for my decision to be astrophysicist was to see what happened and why we are here, why Earth are here, isn't it? Then the evolution of our solar system is very interesting, and can give us also information about another planetary systems now that are known, many solar systems. Another thing that we want to do is to find collaborations with another laboratories that do not the same, but the experiments with minerals, also to see how to improve more, how to improve Citlalmitl also, and how to improve our experiments. Then I hope that the Congress and the conferences will be the next year more normal. Yeah. And then, well, in the next future, we will continue to prove different profiles and different precursor materials.
Very cool. Very cool. Trish, I want to thank you so much for sharing your lovely paper with us and talking us through it.
No, thank you to you also, because I really enjoy a lot to share the knowledge of the science. Also, I really love the outreach, and I do really a lot of outreach, and then this kind of things and this kind of spaces that you can give us to scientists to share our research are very important for the world.
Yep. For the younger generation, absolutely. All righty. Thank you, Trish. Thank you, everyone, and we will see you on the next one. Bye-bye.
Bye.